Welcome to our module on modeling with the ODD process. In this module, you will learn what the ODD process is, how to describe it, and why it exists in the first place. Then we will use the ODD process to investigate a modeling task. But let's start with the basics. How do you design an agent-based model? Formulating an agent-based model means progressing from the heuristic part of modeling, in which we first think about the problem, data, ideas, and hypotheses, to the first formal and rigorous representation of the model. To formulate a model, we try to write it down in words, diagrams, equations, etc., which requires us to make a series of decisions about the model structure. The first purpose of the full model formulation is to make ourselves think explicitly about all parts of the model. Until we try to write the model down, it is unlikely that we've identified all the decisions we must make in designing it. The second purpose is to communicate the model to the people with whom we work, which usually leads to further discussions and revisions of our model. Then third, we use the formulation as the basis for the model's implementation. But to be translated unambiguously into code, the model description has to be complete and explicit regarding each and every element and aspect of the model. So, what characteristics of an agent-based model do we need to describe in its formulation, and how do we describe them concisely yet clearly? When we use traditional equation-based models, we know exactly how to answer these questions. We write down the equations and their parameter values. But when we use ABMs, these questions are difficult because the models can be more complex and because we do not have a traditional notation such as differential equations. However, a standard protocol for describing ABMs called ODD, which stands for Overview, Design Concepts, and Details, is now widely used. The ODD protocol has proved useful not just for describing ABMs, but also as a framework for thinking about the models as we formulate them. Let's dig deeper into the ODD model. Just as differential equations provide a way to think about and describe mathematical modeling problems, and frequentist and Bayesian theory provide ways to think about statistical modeling problems, the ODD provides a way to both think about and describe agent-based modeling problems. We typically start drafting our model's ODD description for the earliest, often extremely simple version of the model, and then work through the modeling cycle by revising and filling in the ODD parts and updating the code to match it. Or we use the ODD as a way to document what we have tried out in the code and found workable. Usually, it really goes both ways. As a reminder, ODD stands for Overview, Design Concepts, and Details. The ODD protocol starts with three elements that provide an overview of what the model is about and how it is designed, followed by an element of design concepts that depicts the ABM's essential characteristics, and it ends with three elements that provide the details necessary to make the description complete. Let's look at each section in more detail. We're starting with the overview section. The overview section contains three items: purpose and patterns, entity state variables and scales, and process overview and scheduling. Here we're talking about purpose and patterns. Purpose means the clear, concise statement of the question or the problem that we address with the model, like what system are we modeling? What management or scientific question are we trying to answer? It's really important to know a model's purpose because that gives you a roadmap to the rest of the model description. So when we know what problem we're trying to solve, we have a much better expectation of what it should look like. That then translates into patterns, like what criteria will we use to decide when our model is realistic enough to be useful for our purpose. And remember that a model is useful when it reproduces patterns that are driven by the same processes that are important for the problem that the model is designed to solve. So if we're thinking about the children's Easter egg hunts from an earlier video, right? We're looking at similarity in age ranges. We're looking at the detection of egg clusters. We're looking at the negative relation between the search radius and the number of eggs, for example. The second part of the overview section concerns entities, state variables, and scales. Entities are basically like objects. They are the kinds of things that we are representing in our model, and they have variables and attributes that characterize them. Entities can be one or more types of agents. They can be the environment in which the agents live and interact, or they can be the global environment that affects all the agents. Importantly, all agents have state variables. State variables describe the state of the agent at any time. They can be properties of an agent, like a color, or they can be behavioral attributes of an agent, like moves one step to the right. The most important thing is that state variables are always observed. They are not deduced, which means we don't calculate state variables. However, we describe state variables on different scales. The two most frequently used scales are the temporal scale and the spatial scale. The temporal scale represents time in minutes, hours, months, weeks, that kind of thing. The spatial scale represents the space in which we are making our agents move around on our screen. So that can either be a total space, like a total environment, or it can be grid cells or patches that we are changing as the agents act upon specific items in our environment. It really depends on key behaviors and interactions and phenomena. The final part of the overview section is the process overview and scheduling. The process overview contains the processes that change the state variables of our model entities. Here we are answering questions like, what are the model entities doing? What behaviors do the agents execute as our simulated time proceeds? And what updates and changes happen in their environment? Now, we can also include observer processes here. They are not linked to the model, but they're important because they may introduce bias, and they may also explain a certain perspective with which you approach the data that you are receiving as the model proceeds. The schedule part lists the order in which the processes are executed. So it's really a sequence of actions to describe which model entities execute which processes and in what order. That's important to understand because here we're looking at dependencies, right? And for really complex models, you may want to start with pseudocode because it's much easier to describe the execution sequence of your model. That brings us to the biggest section of our ODD, which is the design concept section. The design concept section contains 11 possible design concepts, as you're seeing on the right side of your screen here. This section addresses questions like, what outcomes do the characteristics of the agents and their environment produce? What adaptive decisions do the agents make? If agents make these decisions to increase some sort of measure, what is that measure and how do they increase it? You're also going to want to define whether the model includes collectives, that's groups of agents that have their own behaviors. Like, for example, drivers of sports cars, drivers of electric cars, drivers of motorcycles, that kind of thing. You're also going to need to explain why you have implemented these concepts. So the motivation for each of your decisions is really important to state in this section. The first two important design concepts are the basic principles and emergence. For the basic principles, key questions you're going to want to answer are, what general concepts and theories or hypotheses or modeling approaches have you used for your model? How do they build on previous approaches to solving the same problem, right? How have you incorporated them into your design? Emergence answers the questions about the results and the outcomes and the outputs, right? Which of the results and the outputs emerge from the adaptive behavior of the individuals or of the agents themselves, and which ones come as a result of the rules that have forced the model to produce certain results. Once you have defined your outcomes and results, you're going to want to address adaptation. That is, what adaptive behaviors do the agents have, and why do they have those behaviors, and in what ways can they respond to changes in their environment and changes within themselves? Do they make decisions? If they make decisions, and they most likely will, what kinds of decisions do they make? Are they free to make decisions? That is, do they choose among alternatives and consider what alternative is most beneficial to them, which would be direct objective seeking? Or are they forced to reproduce behavior patterns that you have programmed in, that mirror behavior patterns you have observed in real life situations? That would be indirect objective seeking. And speaking of objectives, of course, you're going to have to define the objectives. For adaptive behaviors that you have modeled as direct objective seeking, which means that an agent gets to select a decision among a number of alternatives based on the maximum benefit of that decision for the agent, you're going to want to talk about what is the measure of the decision. What does success mean? What is a successful decision? What does it look like, right? And how does this objective measure represent the processes that link adaptive behaviors to important variables of the agents and their environment? How do those decisions change or modify the environment? Then also, considering the model's purpose and the real system that it represents, how have you chosen the variables and mechanisms in the objective measure? And how does the agent's current state impact your modeling decisions? Does the objective measure that you have used for a successful decision change as the agent changes? We have just considered the questions around the first 4 big design concepts. And of course, there are 7 more because we have 11 in total. We still have learning, prediction, sensing, interaction, stochasticity, and collectives. And the questions that concern each of these areas are specifically related to how are the agents affected by any of these areas. How does the behavior of these agents change? How does the environment change based on any of these areas? And also, are there any specific groups? Now, you can find more information about this in Table 3.1 of your book or on the next slide. This is Table 3.1 from our book. Please take a look at each of the key questions as they relate to the design concept, because you will, throughout this course, be addressing each of these questions as they relate to your continuously evolving model. The final design concept is, I think, the most important one. It's observation. Observation is related to the purpose and patterns section from the basic principles, as well as to emergence, in which you're defining your outputs, but at a much more physical level. In observation, you are defining how your outputs are supposed to appear on the screen, basically. You are designing the interface, you're designing your graphs, your counts, you're determining the sliders that you're going to need in order to help effectively and efficiently solve the problem that you have described in the earlier sections. And now that we're done with all of our design, we get to go into the details of this design, meaning how do we translate the design into code? That's what our details section of our ODD does. The final details section is really quite straightforward. It contains three parts: initialization, input data, and submodels. The initialization part describes the initial conditions of your model world. That is, how many agents do you have? What are the initialization values for your state variables, for your environment variables? Are any of the variables dependent on each other? That kind of thing. The input data part describes the source of the data that you're using for your model. Are those external data? From what repository do they come? Or is the data simulated within your model? Lastly, the submodels section describes any of the subroutines that you have broken your code into. It's a good idea to always work modular. That means to have several different subprograms that you are then going to collect in a master program schedule so that these subroutines are executed in a process that you are defining in what would be a main program or what would be kind of a master, as I said, schedule. And that completes our ODD. And now let's take a look at an example ODD from our book about the butterfly model. The author starts the purpose and patterns section with what the model design is intended to do. Namely, the model was designed to explore questions about virtual corridors. More specifically, the big question that they're pursuing is butterfly hilltopping behavior and how does it lead to the emergence of virtual corridors. So the big question belongs in the purpose and the pattern section because that is the question, that is the problem statement that the model intends to answer. The entities, state variables, and scales section then talks about how the big question is going to be modeled and with what entities, with what state variables, and on what scales. Here, the model has two kinds of entities, the butterflies and the square patches of land. These are their sizes. Here is how the time steps are set up, and here is how the entities move and change. Lastly, the process overview and scheduling section talks about the number of processes in the model, here just one, and how the process executes or how the processes are scheduled. Here again, the order in which the butterflies execute this action, whether it's important or unimportant, and whether any interaction among the processes exist. In the design concepts section of the ODD, note how the author starts with a basic principle and then ties in as many of the 11 design concepts as are necessary to adequately describe the model, ending with the observation. In the final details section, the author discusses the implementation of the model. In the initialization section, they talk about the topography of the landscape and how the agents are set up and initialized as well. So here, for example, we can see the butterflies are initialized by creating 500 of them and that they're randomly placed into the landscape and so on. Next, are there any input data? There are no input data. However, there is an explanation of why there are no input data because, namely, the environment is assumed to be constant. So this section is still really important. And then finally, the author is talking about the submodels or the subroutines that they have built and how the subroutines connect and how they follow one another in order to make sure that the model is executed successfully. And there you have it, right? We have talked about how modern models tend to be pretty complex, which is why traditional mathematical modeling really has given way to agent-based modeling as a more efficient and effective way to represent the models. That's also why we need a standard structure to describe these complex models, because otherwise we would get completely lost in the details. That standard structure is the ODD protocol overview, design, and details. Note that the design section has 11 points that you will progressively elaborate on throughout this course as your model evolves in complexity as well. And once the model is written in the ODD format, it is really easy to translate it into NetLogo or into any other programming language for that matter, because you have already laid out what you're building, why you're building what you're building, and how you're planning to build what you're building. And here is what you have learned in this module. You have learned how to describe the ODD process and to explain why it is a good idea to use the ODD protocol. You have also used the ODD process to investigate a modeling task, namely the butterfly model. Thank you so much for watching, and I look forward to seeing you in our next video.